Great. Okay, so welcome to this month's training for commercial heat trace. This month we're going to, last month was extranet using our systems, and there's links to all of that out there for you. This month we're going to move into applications and design, and this month specifically of July we're going to do pipe freeze protection. We're going to today talk about heat delivery systems. Next week talk about the controls and communications, and after that we're going to do fire sprinkler specs and layout as well. So with that, as I am certainly not the expert in this, we're going to have Will Loach join us and give us a presentation. One thing I want to point out, though, in presentations prior, I had the phone number wrong, so please note for your commercial heat trace contacts, that's them as, of course, you've got Gordon, Chris, Ryan, Will, who'll be speaking shortly, and myself. I just wanted to point out to everyone I did have the wrong phone number in there, and that was my fault. So please take note. That will be corrected going forward. And with that, I am going to hand it over to Will, who's going to tell us all about heat delivery systems for pipe freeze protection. And Will, if you're ready, I'm going to hand it off to you, okay?
Sounds good. Thank you, Derek. So as Derek mentioned, I'm Will Loach, RTSM for commercial heat tracing, primarily in the Northeast region. I sit on the north side of Lake Ontario, about halfway between Toronto and Montreal, and my activity radiates out from there. So, but anybody, feel free to reach out with any questions you might have, or if you need help with a project. There's my information. It'll show up again a couple times in the presentation. So today we're going to be looking at basically plumbing and heating, ventilation, air conditioning, piping, freeze protection. The reason I make that distinction is that fire sprinkler has some special considerations that we'll get into a little deeper in a couple weeks. Yeah, we'll leave that aside, but we're talking general application pipe freeze protection today. So we'll kind of look at what makes up a heat tracing, a pipe freeze protection system, the components of the system, what the guidelines are from the industry standards, a couple comments on the types of inquiries we get in the commercial heat tracing market, and then dive right into actually selecting parts and building a bill of materials and the kind of thought processes that go into that. And then again, we'll review the training schedule for the rest of July. So without further ado, we can, this is a pretty simple schematic that we've drawn a few of these for different types of heat tracing systems. This one would be kind of a fairly basic pipe freeze protection system. And if we think about it, really there are two parts to any pipe freeze protection system. Got the heat delivery component, which is we're putting heating cable on the pipe, we're delivering heat to the pipe, and then the control and communication component, which is where we're turning the heating cable on and off using some kind of sensing and switching devices, as well as communicating status to some remote location in some way. So that'll be addressed next week. I have July 26th on here, but we're actually going to do that one next week. Heat delivery is today. Okay, so the heat delivery parts would be the heating cable, the connectors, T's and N seals, and the fastening equipment. And like I mentioned, control and communication would be the sensing devices, switching devices, and then any kind of data monitoring and reporting to elsewhere. Just for a bit of background, all of the recommendations that we make and most other heat tracing manufacturers make or should be making come from IEEE 5151-2012. IEEE is the Institute of Electrical and Electronics Engineers. This is a standards document, so just important to understand that terminology. So a standard is kind of a guiding document. They're generally generated by manufacturers and third parties in committee, and they kind of outline the recommended best practices for either manufacturing equipment or designing systems. A code is a legal building requirement. They are governed by authorities having jurisdiction. Standards and codes will often make reference to each other. They will sometimes contradict each other. The code is generally going to rule over a standard, but the standard often influences the content of a code. That's just so you understand what that language means, and so you can talk the talk when you're discussing these systems with people. Standards will generally outline requirements for products and systems. So they'll define the product characteristics, recommendations for testing procedures to ensure that the products do what we say they're going to do and will not fail under standard conditions. And then the system performance guidelines kind of define what you do to implement those products in the field, the various parts, how you're going to set them up, how they get installed, how they get controlled. Okay. In the commercial construction market, decisions tend to be made very quickly. We're often under the gun to get answers back to people in a very rapid timeline. So there's kind of three general sets of inquiries we might get. And I put selfies on here to kind of show you my emotional state when I'm presented with each scenario. So, happy and relaxed when I'm at a project design meeting with engineers, and they just throw a set of piping plans on the table and say, we're going to trace all this piping here. Could you give us some recommendations on what equipment we should specify, what the electrical load requirements might be? And we don't need an answer till the end of next week. That's great. I can take my time. I can do everything properly, influence the specification, and set the bidding parameters up, in a way that's ideal for me. Second scenario is a phone call from some contractor standing on a job site looking at two 8-inch cooling tower pipes about 40 feet long, and they want a quick price, and that's cowboy mode. You've got some rough numbers in your head. You give them a budget that they can present to their clients and then come back to you for details later. And then the third, which comes up more often than it should, which is that late afternoon email from a contractor. They need a quote by 9 a.m. tomorrow, and they sent you a link to a Dropbox folder, which has a PDF document 600 pages long, and you got to sift through and pick out the lines. And that's where I'm a little bit stressed out and frustrated, because I got to spend about 4 hours in the dungeon scaling things off of drawings. But all of them are great opportunities, and the better we can serve them, the more successful we're all going to be. So we'll talk about how we address each of those concerns right now. So again, just to come back to it, today we're going to look at the heat delivery component of a pipe freeze protection system. So that's the putting the right cable on the pipe, putting the right accessories on the cable to make sure that we're creating a codes and standards compliant system, and then fastening it properly. We'll kind of look at, as far as the heating cable goes, we've got to select the heat output, we've got to select the voltage, we've got to select the jacket, and then figure out how much of each cable that we've selected that we're going to need. For connectors, T's and N seals, and tape and labels is basically how many and what kind. And it's not overly complicated, but there are some rules to follow and things to think about. So the heating cable that we're going to use for pipe freeze protection is going to be our CPR, self-regulating cable. That CPR stands for Commercial Pipe and Roof. We've got it cross-listed for a handful of applications. As you can see here, I've kind of color-coded the blanks that get filled in to generate a part number. So the first one is the wattage. We have a 3, 5, 8, 10, and 15 watts per foot. Those are nominal values. They're pinned to the heat output of the cable at 120 or 240 volt at 50 degrees Fahrenheit. Just a note on that, you can see on the right, I've got two tables or graphs showing the cable heat outputs on metal versus plastic pipe across a range of temperatures. So these are self-regulating heating cables. And what that means is, if you look at left, that graphic in the upper left is kind of a cutaway image of the heating cable itself. So A is pointing to the bus wires. They're what carry the power through the heating cable. This is a parallel heating element. So there's basically an infinite number, if you're thinking about it electrically, an infinite number of parallel heating circuits along the length of this heating cable. current is passing between the two bus wires there, which are embedded in a semiconductive polymer core material. That polymer core has different amounts of carbon black embedded in it. And so what goes on is the heat is generated. As the core warms up, the carbon black more or less expands, increases the resistance between the two bus wires, so the heat output goes down by Ohm's law. So what that means is we don't have to worry too much about controlling the cable tightly, because it's going to modulate the amount of heat that it's producing as it warms up. So we've mitigated, if not eliminated, the risk of the heating cable overheating itself. The rest of the cable is just physical stuff. So item C is a polyolefin jacket. That's an insulating jacket between the core and the grounding braid, which is item D. D is that, like I mentioned, it's a grounding braid. It's continuous along the length. So if there were any fault in the jacket, it would current would be interrupted at the braid before it reached the surroundings and energized a network of piping, which would be a big problem in a building that trips the ground fault and shuts the cable off. E is the outer protective jacket. Both of our jacket options are rated more or less to the same set of product standards, but there are some specific properties that I'll get into in a little bit. So right now, the first question is the heat output. Do we need a 3 watt, a 5 watt, an 8 watt, a 10 watt, or a 15 watt per foot cable? So just to bring this up from first principles, ultimately what we do when we're selecting a heated cable is we're trying to balance the heat being lost by the pipe to the surroundings with the heat that we're going to deliver back onto the pipe with the heating cable. So you reach back through the cobwebs in your brain to high school physics and chemistry. At its core, what we do is a heat loss calculation. So we've got the heat is determined by the mass, the heat transfer coefficient, or the specific heat capacity of the system, and the change in temperature. So, like I mentioned, heat loss to surroundings and heat replaced by the heat tracing, that's our Q. Mass is largely governed by the diameter of the pipe and the material of the pipe and the properties of the fluid inside the pipe, whether the pipe is full or not. The heat transfer coefficient is going to be governed by the fluid's properties, the material of the pipe, the insulation type and thickness, and whether there's any wind wicking heat away from the outside of the insulation. You can get really granular and look at this value as it applies between the fluid and the pipe wall, through the pipe wall itself, between the pipe wall and the thin layer of air between the pipe and the insulation, through the insulation, and through the outside of the insulation. But really, we just consider this whole thing as a system. And then what we're trying to do is offset the heat that's lost as a result of the difference in temperature between our maintained temperature, which is where we need to keep the fluid inside the pipe, and the ambient temperature, which is the temperature in the surroundings around the outside of the insulation. Don't worry, you don't have to do all of this science and math every time. I mean, obviously that would be impossible in today's environment. So IEEE 5151, that standards document that I mentioned, has guidelines for outdoor freeze protection in watts per meter, conveniently, based on the use of glass fiber insulation. So they're already starting to narrow down our parameters for us. They published this table. They give some correction factors for the insulation, various different insulation types. We take that data and build software for making these calculations. It's called Chromatrace. Some of you will have heard this before, but there is an update coming for commercial applications. For now, we're doing things a little bit old school. So remember, all of those parameters dependent on a whole bunch of different things. We in the commercial environment, since we're mostly dealing with water, can narrow a lot of these down. So our fluid properties aren't going to change from situation to situation. It's water, it's in a pipe. The insulation type is usually going to be standard fiberglass. We're largely talking about above ground piping today. The insulation thickness is going to depend on the individual engineer's specification. We can make recommendations when we need to, but usually they've got a spec book, and it's outside of our control what the contractors are going to do with insulating the heat trace lines on a project. We can influence it, but usually they'll just defer to the insulation schedule because that's often a different contractor from the mechanical contractor themselves. There are guidelines in IEEE 5151 about what thicknesses of insulation should be used to optimize the heat tracing system, but they aren't always carried through to engineers' specifications. So always check that spec book or ask the customer how thick the insulation is that they're going to use. And then the minimum ambient temperature just depends on where the project is and how cold it gets there. There are guideline tables in various sources, and our software and design guides will kind of give you a recommended minimum ambient. I'll usually just go to Wikipedia, look at the climate data for the city that the project is in, and use that. So this is a new document we've created. It's not quite ready for prime time, but the idea here is to give you a chart and make it easy and fast to answer the contractor's questions. So you need to know, like I said, pipe size, insulation thickness, minimum ambient. We've picked 4 nice round numbers in Fahrenheit: 20 Fahrenheit, 0 Fahrenheit, minus 20 Fahrenheit, minus 40 Fahrenheit as our minimum ambient temperature options. And then just Ryan Conway ran the 360 chromatrace scenarios necessary to pick our cable wattages according to various pipe sizes and various insulation thicknesses. So this makes it pretty simple. Your contractor will say, I've got a 4-inch pipe with 1-inch insulation, and you know it's in Montreal. So it gets pretty cold in Montreal. We're going to go all the way over to the right. The pipe is a metal pipe. CPR8 is our answer. Just so that you understand the shortcuts we've taken. So I mentioned that self-regulating property and that we and Ohm's law as well. So we used 208 volt supply as the basis for selection of all of these heaters, and that puts us at the low end of our heater output range, which means in some instances, if the project voltage is 277, you might be able to get away with using a lower wattage cable, but this will give you a safe answer. Our priority is to, our mission here is to sell heating cable, but it's very important that we not freeze a pipe by cutting a corner. So this table will keep you reliable. We've also used outdoor conditions and 20-mile-per-hour wind, so we have a pretty ugly heat loss situation on the outside of the insulation. For the metal pipe material, we wanted to reflect the most common applications at given diameters, so we used copper up to 3-inch. That's your domestic water services. Cast iron or ductile iron for 4-inch and 6-inch pipes. Those will be sanitary drains. And then steel for larger piping, because that's what we'd see on cooling tower systems. This isn't, those pipe materials aren't really critical. They don't make a huge difference in the amount of heat loss, but we just thought, why not publish this way, because it sort of reflects what's going on in reality. Another thing that you should note is in some cases we'll say 2x CPR8 or 3x CPR8, and that indicates the trace ratio. So when a single run of cable is insufficient, we just start running multiple runs of cable. We do not spiral heating cable along the pipe, although it might be less expensive on a foot-for-foot basis to sell the product like that. It is a bear to install cable spiraled around the pipe. They have to figure out a way to make sure that they use exactly the same ratio, the spiral ratio along the length of pipe. It's physically impossible without spending a ton of time. And it also can create problems down the road where as the heating cable warms and cools, it will expand and contract a little bit and start moving and migrating along the pipe, wiggling. And you can have cable all piled up at one end eventually, and that's not doing anybody any good. Another thing to understand about this is that we use CPR8 as our maximum heat output on plastic pipes to keep the contact temperature down between the cable and the pipe wall. That's because plastic pipes will soften a little bit if they're exposed to high temperatures. So we move to multiple runs of heating cable sooner on the plastic pipes than we do on the metal pipes. We've done some in-house testing, and we saw that there was a little bit of discoloration when 10-watt cable is installed on a plastic pipe, so we just thought, well, we'll stick with 8 watts. It seems to be an industry standard, and not deviate from that. A few talking points for when you have this document in your hands, which should be in the next few days. You'll notice it's color-coded, so you can sort of see visually the darker the color, the more intense the cable we're using. Right away, what'll jump out is when there's more insulation, you need less heat. That makes sense, right? You'll notice that we go to higher wattages on plastic pipe in a few cases than we have on metal pipe. And that's because of that heating cable's self-regulating property. Just remember that plastic is a thermal insulator. So the heating cable warms itself up faster on a plastic pipe than on a metal pipe. It'll get to higher temperature, which reduces its heat output. So we have to compensate for that by using a higher wattage cable on plastic pipe than we do on metal. And just for clarity, the spiral run image, if you didn't understand what I was talking about there, that would be the scenario where the cable's being wrapped in a spiral around the pipe instead of applied linearly across the bottom of it. So there you go. We've made it pretty easy to pick the cable wattage. Next question would be the cable voltage. So usually you just ask. That's either going to be given to you right up front with the request for quote, or it's going to be in the spec book for the project or in electrical panel schedules. That information is not usually too hard to find. The cable itself is going to be the same price, whether it's 120 or 208 or 240 or 277. So, price, the cost of the product itself isn't a consideration. At higher voltage within a given cable family, so say in the 2 series, 208, 240, 277, we will have higher heat output. So again, back to that cable selection chart, that's all based on 208 volt, which keeps you reliable, but might mean that you're selecting a higher wattage cable than you might necessarily need. That's okay. For pricing purposes, you get the right number in the book, and if they buy it and you don't have any input later, you're not going to freeze the pipe. If you need to try and find a more efficient design and you know that the project is operating at 240 or 277, you can do that and do a little bit more of extra work down the road. Higher voltages will give you longer circuit lengths. So this chart down below is a maximum circuit length chart. Just notice I picked arbitrarily the 5-watt cable, -1 for 120, -2 for 208 to 277. We can put 4 feet of the 208 to 277 cable on a given breaker size than we can on the 120 volt cable. That's pretty obvious. The only cases where I would propose 120 volt to a client would be for short runs or retrofit cases where there's already a 120 volt supply near where a heat tracing cable is about to be installed. And, provided they've checked their load is acceptable, you just peel power off of that rooftop receptacle over to the condensate trap and trace it with 120 volt cable. So that solves the second question. And the next one is going to be the jacket material. It's pretty straightforward. It's outlined on our data sheet. Like I mentioned, both the CR, which is a TPR or polyolefin type of polymer, and the CT, which is a fluoropolymer, more robust material. Both of them satisfy the same set of criteria under our third-party listings. They're both UV stabilized. They're both resistant to moisture ingress. They're according to standards, they're basically the same. According to IEEE 515, there are certain cases where we should be using the CT jacket. If you want an easy way to remember, just see the T, think of Teflon. It's a tougher material. It is more resistant to attacks from organic compounds, so it will resist exposure to oils and fats and greases, and as well heavy exposure to moisture. So we promote the CT jacket. Aside from roof and gutter applications, we promote it for buried piping and for oil and grease piping. The scope of today's presentation is above ground water piping, so we'll be largely living in the CR world. As a quick reference, there's about $1 per foot landed cost difference between CR and CT. So I would say do not use CT as the basis of all of your bids just to cover any doubt, because that's going to make you a lot less competitive on things. But just be aware of what that difference means and where we use one versus the other. Okay, great. So we've built our cable part number, CPR, wattage, voltage, jacket. Now how much of it do we need? Again, we got to start making decisions. Remember that we have this range of 5 heat outputs so that we can pick the right wattage to offset heat loss on a straight run basis. So we're using a foot of cable per foot of pipe as our starting point, unless we're doing multiple runs, in which case you're doing 2 feet of cable or 3 feet of cable per foot of pipe. Power kits and tees and end seals, which I'll talk about next, we generally suggest adding 3 feet of cable for each of those that shows up in the bill of materials. And that is to allow for a couple things. First, it gives the contractor an opportunity to cut off a bad termination if they've made a bad termination during the installation process. It also allows for the implementation of a service loop at every termination, which is where we install spare cable on the pipe at each termination location for future maintenance. If they need to come along and install a branch of pipe there's a bit of spare cable to pull off the power kit and install a T if they need it. People will, well, they probably won't, but they'll be thinking, hey, that rep who told us to put the 3 feet of cable here, we should buy that guy a beer because they saved us trouble down the road. Another consideration is areas of additional heat loss. So elbows, valves, flanges, and pipe supports are all places where the insulation becomes a little bit less reliable because there's a hole in it that allows the penetration of the piece of equipment, or there's 2 pieces of insulation of different diameters joined together. So really any irregularity in the pipe run is going to be a point where the localized heat loss is increased. So we have to add a little bit of cable to offset that. We've got details and some guidance in various documentation pieces about the cable adders for various types of these irregularities. Here are a couple of valves. There's the detail on how to handle a pipe elbow. For commercial construction, you don't have time to go through with a fine-tooth comb and understand all of those things in a pipe network. Feel free to do it if that's the way you want to do it. For me, I just multiply my total cable count by 1.1, so I'm adding 10% of heating cable versus what I think might have been necessary, and I move on to the next inquiry. And that has never done me wrong. So these length details might come directly from the contractor. Remember that phone call, 40 feet of 8-inch pipe. For that 40 feet of 8-inch pipe, I'm going to think in my head 40 plus I've got a power kit, so 43 plus an end seal, 46 times 1.1, I'm going to try and sell them about 52 feet of cable. Or you scale the lengths from the plans, or you go to the job site with a measuring wheel and you walk the entire length of pipe, taking note of various diameters if that's the way it's going. Just always keep in mind that the installer's labor is worth more than your heating cable. So it's better to sell them a little bit too much stuff than it is to go right down to the nickel on the amount of cable, and then they run out because of something that we didn't know about when we were proposing the bill of materials, and they have to send someone to the shop to get more heat trace. Just remember that labor cost is significant. Project managers will thank you, and they're the ones we need to keep happy. Here's a little graphic on the service loop. So that's what I was talking about there. We run the heating cable. This isn't exactly the connection kit that we use, but you run the heating cable past it, maybe back a little bit, and then come into the heating cable. It's just there, again, for the termination process during installation and for future maintenance. Another thing to notice that shows up on this graphic and is fairly important, it's not going to influence our takeoffs in any way, but when you're talking to installers, just make them aware that it's best practice to install a conduit drain. And actually, after Derek and I talked about this, I went and a similar detail is in the IEEE 515-1 document recommending this conduit drain. And the idea there is that if water somehow gets into the power supply conduit network, we've given it a place to escape before it gets into our termination kit. If you think about that cutaway image of the heating cable, water will migrate down the inside of the jacket in a heating cable and create problems, because as the cable expands, that water will expand a little bit, and that can start to compromise not only the heating properties of the cable itself, but will also contaminate other connection kits in the heat trace cable run. Moving on, connectors, T's, and end seals. How many of them and what kind? So we've got pretty much for freeze protection piping, we're using our DL series kits right now. The power connection kit is RTPC, PC power connection. All of these components are part of the listed heat tracing system. Do not sell heating cable without these things. It's an approved transition point between the building wire that's bringing the power to the system and the heating cable. They're NEMA 4X rated. They're mounted on the pipe, and then they kind of sit above the insulation. For access to them, you'd need one of them per distinct run of pipe or per heat tracing circuit. I'll come back to what I mean by a heat tracing circuit in a second. Add a pipe strap. It's a separate line item. The pipe strap you can see in the little graphic in the upper right. It's what holds the kit in place on the pipe. So again, you're using the pipe diameter information to determine which strap you need to go with the power kit. T-kit, RTST, or Splice NT, they'll splice together 2 or 3 pieces of heating cable. So they'll be used either when there's a branch off of the pipe that's being traced and you need to peel off to the side with a leg of heating cable, or if you just use them as required when joining 2 pieces of heating cable. So if the installer, say, underestimates or just had a 1,000-foot spool and they're tracing 1,200 feet of pipe, they're going to run out. They don't want to just take everything off and start all over again, so they can just use a splice kit there to join the 2 pieces together. Again, add a pipe strap to the bill of materials for each kit. End seal kits close off the dead end of the heat trace cable run. They sit below the insulation. So your logic for determining how many end seal kits you need is 1 per power connection and 1 per splice or T kit. So the T will open up another open end of heating cable that needs to be closed off by the end seal. Then I'd come back to what a heat tracing circuit is. So every separate run of heat tracing cable can be defined as a circuit, a heat tracing circuit. Although you might have several heat tracing circuits sharing a circuit breaker, provided that the total load and your control methods allow that. A heat trace circuit might also be referred to as a loop or a point. It really depends on regional preferences, terminology that you might hear. So what's below here, again, is the maximum circuit length chart. Basically, if your run of pipe is going to exceed the length allowed on the given circuit size, which has been determined earlier in the process, at the given voltage, which again has been determined probably by someone else, you add your power kits and end seals accordingly. So I alluded to this being subject to control considerations. So we'll get into that in the next presentation module, but not all of our controls equipment has the same current ratings. So depending on the types of controls that are being used, you may have to adjust the maximum circuit lengths. Just as a sidebar, 40 amp circuits are extremely rare in the commercial world. If you have to guess, I'd say 20 amps is pretty safe because that's going to be below what our controllers can handle. Most common is probably 30 amps, but again, it depends on the project. So fasteners, these are probably the easiest ones to figure out. So we've got two types of tape. FT66 fiberglass tape is the most common one. This is the one that we use to band the heating cable to metal pipes. It's purely a fastener. We would wrap it around the cable every 3 feet. And as you might imagine, bigger pipe is going to take more tape. Your circumference calculation, 2 pi r. If you want to get right down to it and calculate how many inches of tape you need, go for it. Otherwise, just have a look at the data sheet this is on the heat trace accessories data sheet. FT66 fiberglass tape has a little table under it telling you how many rolls of tape you need per 100 feet of pipe at a given pipe diameter. This stops, you'll notice, at 12-inch pipe, and that's probably because it starts to become more efficient to use AT18 aluminum tape on very large diameter piping. The reason for that is that the AT18 is applied linearly along the length of heating cable. We use it largely on plastic pipe because it'll improve the heat transfer between the heating cable and the pipe wall. Holds the cable in constant contact with the pipe, and because we're applying it linearly, the math is a little easier. A 180-foot roll of tape for every 180 feet or so of heating cable will do the job. Warning labels come in a pack of 5. WL05 is the catalog number for those. They are an electrical code requirement. The idea there is that the outside of the pipe is labeled as an electrically heat traced device, so that if someone comes along, say a plumber comes along with a Sawzall, they don't shock themselves when they go to cut the pipe up. Stick them on the outside of the insulation, 1 sticker for every 10 feet of pipe. So naturally, 1 pack of these of 5 labels per 50 feet of pipe. Pretty simple stuff. So again, that should help you with the quick inquiries or the inquiries where you have time. When a project is larger and you have to be you're dealing with multiple runs at a huge variety of diameters and a large number of circuits, I like to use software called Bluebeam. So this is design software that's pretty widespread in the construction industry. Contractors and engineers use it for passing information back and forth. It's pretty intuitive software, and it's extremely powerful. So the way I use it for heat tracing on larger projects is page by page, go through, calibrate the scale on the page. So it allows you to apply a physical scale to a PDF document, and then there are various measuring tools available. So I use the perimeter tool to draw along the lengths of pipe, just clicking at every change in direction of the pipe run. and then go into the properties of the perimeter run measurement that I've just taken, tag it with some information. I use the protocol HT and then an indexed numbering. I learned the hard way to use 3 digits instead of 2 digits on a big project one time. Dash OD, so that's like 02 for a 2-inch pipe, 50 for a 50 millimeter pipe if I'm working with a Canadian engineer, and then a dash and the type. The reason that I use those 3 bits of information is that the first one is just a pipe, a heat trace loop identification tag. So you can go and find it in the plans if you need to say, hey, what's the deal with the HT056? I put the outer diameter in there because when in the next step it allows me to select a heating cable automatically, and then the type because we might have mixed plumbing, drainage, fire protection, and heating, ventilation, air conditioning plans, and they might be under separate scopes of work, so that allows me to filter that. So we can export. You see down at the bottom of the screen, there's a handful of the markup records. So all of those markups can then be exported from Bluebeam to a CSV file. So you trace everything out, export to CSV, flip that to an Excel file, and start applying some logic to that spreadsheet, and you can get a pretty big job done in a relatively small amount of time for budgetary purposes, and then come back to that later when it's time to refine everything and place a purchase order. So again, Bluebeam is a very powerful collaborative technical communication and design tool. Engineers and contractors use it, so if you're using it, they'll be impressed, and because you can communicate in the same protocol, you're speaking the same language and walking the walk with them. Another important function that it serves is it defines the scope that is covered by a bill of materials or a quote that you send out. So I'll send the markup file that I use to generate a bill of materials to the contractor along with the bill of materials and the quote, and be very clear, hey, here's your price, here's the bill of materials. Attached PDF indicates the runs of pipe that I'm tracing, because there's quite often engineering isn't done 100% accurate. So it's important to communicate what it is that your price applies to, and be clear, this is what I've covered in this quote. If I've missed anything, let me know. Just understand, I've told you what my quote is for, and so now don't come crying later if I missed a pipe run or if they added something and it wasn't covered by this. It's also a future reference because in a lot of cases we will bid a project and then it goes away for 2 years and then comes back when it's time, when they've dug 4 levels of underground parking and it's time to start tracing pipes. You're never going to be able to remember what you did. So it's really helpful to have that layout from bid stage available as a reference for now that it's construction and purchasing stage. That can save you all kinds of hassle down the road. So I am a strong endorser of Bluebeam. If anyone wants to talk more about that, please reach out. It's partially I'm offering the service of training on the software because it'll make all of you better at what you do, and also on a selfish basis, it'll mean that Ryan and I don't have to do it for you as often. So I strongly encourage download the Bluebeam 30-day trial, play with it a little bit. I use it as my default PDF viewer now, just because there's so much that you can do with it that makes life a lot easier than Adobe Acrobat. And another word on the upcoming training, we're changing the schedule for July around, so next week will be our control and communication overview, kind of outlining our good, better, best scenarios and how they relate to recommendations we can make to consulting engineers, as well as what they're based on from IEEE 5151. And then at the end of the month, we'll cover fire sprinkler pipe freeze protection because it has special considerations that are different from anything else we do with pipe freeze protection. Again, there's my contact information, Will Loach. I'm up in the Northeast. If you need anything, don't hesitate to call. And I guess now I'll pass back to Derek.
Oh, I got it, Will. No, that's great.
Perfect.
Yeah. And like Will said, that's his contact information. You know, this is Will. He's our commercial heat trace expert here at Chromalox. So, you know, he's the man for design and all that. I really appreciate that, Will. We'll open up for questions here in a moment. As Will mentioned, the training is just flipped a little bit. We're going to do controls next week and then fire sprinkler on the 26th. Same invites. If you already accepted them, don't worry about it. Please attend. I'll send them out again with the summary and the update or the follow-up from today's presentation. Dropbox is up and running. YouTube channel is there, so please subscribe. When things get posted, you'll get them. So if you missed them, you can go watch it anytime you want and for reference. And again, Will, thank you so much. I think at this point I'm going to stop the recorder and open it